And here we go. All right. Just as a review, we started talking last time. We talked about Eulerian versus Lagrangian descriptions of the fluid. Would somebody, let's say Connor Anderson. Hey, Connor, would you give us a brief description of the Eulerian versus the Lagrangian ways of viewing the fluid?
Well, the Lagrangian way of viewing the fluid is you basically look at a specific fluid particle, and you follow that fluid particle around. The Eulerian way of viewing the fluid is you, I think it's a little bit hard to describe, but you look at a section of the fluid and you kind of divide it into different vectors that way.
Yeah, it's sort of like you look at just an area with fluid in it, and you look at properties just as a function over that area. Let's say that, okay? Rather than following a specific piece of fluid around, right? And we talked about this material derivative, which is a way of sort of putting together those, connecting those two ways of viewing the fluid. So you, for some property F, you have how F changes for a fluid particle, the rate of change, how the field itself in a Eulerian way changes with time, how the fluid particle moves through the field because with that velocity field, and then how F changes in each direction. Talked about that. Okay. Today, we're going to talk about something called the Reynolds transport theorem. This is a general way to set up material balances. What is a material balance? Does someone have a thought on what a material balance is?
All right, can I ask a question about the material derivative real quick?
Sure.
So are you ever going to be able to be going at a velocity that's different than the velocity of the fluid?
No, so the velocity, this velocity is a velocity field of fluid. So this wouldn't work with anything that is not going at the same velocity as the fluid. That's why in examples we use like a really light probe or like a leaf, something like that, something we can assume is just moving at the same velocity of the fluid. And of course, if it's just a fluid particle, so it's just a piece of the fluid, it would be moving at the same velocity.
Okay, thank you.
Good. All right. What's a material balance?
Is it basically just in minus out, like the accumulation equals in minus out plus generation?
Basically it is IOGA, okay? But so a material balance is balances of things like mass or moles or energy or momentum, anything where there's sort of an amount of stuff that's maybe flowing in and out and accumulating and being generated or destroyed, all that junk. Okay, so we're going to discuss the theory of this in the Reynolds transport theorem very briefly, and then we're going to apply it to mass balances and simplify. And then we're going to talk about mass balances, and we're going to talk about transient mass balances with an example. What does transient mean here? Did anyone know?
Changing.
Changing. Transient means changing, specifically changing with time. Okay? Y'all should know how to do steady state mass balances because you should have covered that in 170 and 273. So in this class, we're going to cover non-steady state mass balances. Yeah. All right, now before we get to this, there's a couple different ways, again, to look at these balances. So a system is a certain amount of mass, and then you can follow that amount of mass and see what happens to it. And then a control volume is when you define a volume in space and then mass can flow into it and out of it. In this picture, which I took from your book, you could think of this is a can of deodorant. So the spray would be the system and you could follow it as it gets sprayed out, whereas the control volume would be the can, the volume of the can. Right? And you can think of this as sort of like the Eulerian versus Lagrangian ways of looking at things we talked about last time, right? So the system would be more like the Lagrangian way of looking at things. You're following a specific piece of the fluid as it moves around. And the control volume is more of the Eulerian way of looking at things, where you define a specific region. Peter asks, okay, maybe we'll talk about that later. I want us to keep going. Had a good question though. All right. So again, sort of thinking about that. You have some control volume. You call the surface around the control volume the control surface. So stuff can flow into, over, and out over that surface. So you have mass, you have some kind of mass, and the mass can be carrying with it energy, momentum, whatever. It's going to flow in and out over that surface. Also, the control volume itself can change shape and size. What would be an example you can think of where what we might consider a control volume might change its shape and size?
A balloon?
A balloon, right? That's a really good example. As air is let out of the balloon, the volume of the balloon will change. Or, yeah, e.g. a balloon blowing up or being blown, either way. All right, so just like the material derivative kind of gave us a mathematical way of relating what happens to a fluid particle with what's happening in the sort of the Eulerian view of the field, the Reynolds transport theorem sort of relates what's happening to a system, so a certain amount of something, some material property like energy or momentum or whatever, and what's happening to the control volume. That's the link. This is it. This is the Reynolds transport theorem. What does all this junk mean? Okay, so B is any extensive property. What does extensive property mean? That's a term you might have heard in physics class.
Would an extensive property be one that depends on how much of something you have?
Yes, exactly.
Like mass?
So pressure, for example, is not an extensive property, right? Because I could have a 2 feet deep pool of water that's 1 foot across and a 2 foot deep pool of water that's a mile across, and they both have the same pressure, right? Not an extensive property. Whereas mass, momentum, energy, all of those things, the more stuff you have, the more property you have. Okay, that's all it means. So then little b is just big B over M. And N, with this bar on it, that is a vector normal to the control surface. The important thing there is that V dot N, that's just mass speak for velocity going in and out of the surface. So that's what that means. So then what physically is this? Okay, so dB dt is the total change of the amount of property in the system. Now, I believe, Tyler, you talked about input, output, accumulation, generation. Which of those is this?
To be honest, I don't know.
Okay, so you have like a total amount of something, let's say energy, right? So let's say you have some reaction and it has, there's like 1,000 joules of energy, and the reaction happens and you get another 1,000 joules of energy per time, right? What is that? Is that generation or accumulation.
So if it's, okay, I'm a little confused, but if the energy is leaving the system.
Okay, leaving the system, it can just flow in and out, right? So generation in that thing, it means it's being created or destroyed. So that would be like if mole A is turning into mole B with the reaction, or if energy is being created by an exothermic reaction, something like that. Okay, that's what that's talking about, generation.
Okay.
Okay, because you have a total amount of whatever that's tied to this particular amount of mass, and that whatever can be created or destroyed. That's what that is. Okay, so this next bit then, this is change happening inside the control volume. Because change can be happening with time, and we're integrating density over we're integrating over the control volume, so that's what that is. Change happening inside the control volume. So is that accumulation or output input? Do you think?
Accumulation.
Accumulation, right? That's accumulation. Because we're just, imagine a tank and mass, let's say, could be building up in it or dropping down in it. That's accumulation. That's what that means. And so that would mean that this last one, which is flow in and out across the control surface, that's input output. So yeah, Avonlea asks, does dB dt represent generation and consumption terms in one? Yes. Generation would be positive, consumption would be negative. Okay. Right, and as you can see what that's doing, this is an integral across the surface. Because stuff flows in and out across the surface. This is an integral across the volume. All right, so this is the most general possible form of this. This could be used for all kinds of super complicated problems where it's compressible flow, so the density is changing and there's crazy things happening at the surface, all sorts of things. But we are going to simplify it down before we do any problems with it. I'm gonna let you go. I do want you to write it all down. Okay. We're going to simplify this down for mass balances. So the thing that we're doing a balance on is mass. So what is capital B?
M.
Nicholas asked, is V dot n a scalar or a vector? Practically, and everything we were doing is going to turn into a scalar, you'll see. M. E is M. All right. So then what's little b?
1.
1. All right. This is the trick. What's dB system dt for mass?
0?
0. What's that, Connor?
Yes.
Why is it 0, Connor?
Because you can't create or destroy mass unless if you're doing nuclear reactions.
Yep, it's because mass isn't created or destroyed. Again, if we were nuclear engineers, maybe we'd deal with that. But for us, mass is neither created nor destroyed. So the system is a certain amount of mass, and that certain amount of mass is not, that certain amount of mass is just going to stay constant because mass is conserved. That's the conservation of mass for you. So. And so there we go. So looking at this, it's been so over here we have rho times dV. So imagine a tiny differential cube of volume or whatever. So rho times V, rho times the volume of that little tiny bit. What's that? What's density times volume? Okay, Peter asked what CV and CF. CV is the control volume. So this is just the volume of space we're looking at. And CS is the control surface. So that's just the surface around that volume. Okay. All right, so density times volume, what do you get?
Mass?
Mass. Thank you, Connor. So the density times that little differential volume would be mass. You add it up over the whole volume. What you get is the total amount of mass in the control volume. dm dt. If you want, you could put a little CV to remind yourself that this is a mass in the control volume, but a lot of times you'll just say dm dt. And now let's look at this. So B dot n is just going to turn into the velocity. The n, as I said, all that does is it just takes the velocity that's either going in or out over the surface. That's what that does. So a velocity times an area, what's that?
Volumetric flow rate.
Volumetric flow rate. So that would give us, okay, and then a density times a volumetric flow rate. What does that give us?
Mass flow rate.
Mass flow rate. Okay, so this just turns into mass flow rate. And it's going to be m dot out minus m dot in. That n vector is what makes the out be positive and the in be negative, but I don't think we need to spend a lot of time thinking about that. All right. The n is, so like this is the control surface, and so n is it's just the vector that shows it's the direction normal to that surface. So it just shows what stuff is flowing out that way. All right. You get this. Now, some of you may vaguely remember doing mass balance problems, sort of like this in calculus class. Sometimes calculus will have mass balance problems like this as an example. Now, as I also said, y'all have done mass balance problems in your 170 class and in your 273 class before. So let's do a little review. I have a problem for us. Okay, yeah, mass within a control volume, mass in and out. All right, I've launched a poll. With possible answers to this, should be able to do it pretty quickly. All right, I think there's two students who haven't voted. Gonna give them until 55 seconds. All right, so we have unanimous, that is 3 pound mass per second, which is the right answer. Okay, as I said, pretty simple, and you were able to do that so quickly because this was a steady state problem. So what does it being steady state mean?
Your in equals your out.
It means M in equals M out because it's steady state, there's no accumulation. The mass inside, what would be our control volume here? Be the stirrer, right? So the mass inside that stirrer is not going to change with time. There we go. Okay. But now let's do a transient problem. And that's what we're going to spend the rest of the class on it. We're just going to do this example problem and we'll talk about it and any questions you have. So we start with a cylindrical water tank of radius r, whose top is open to the atmosphere. It's filled with water to a height h0. A plug is pulled on the bottom, so the water begins to drain out through a hole. Let's assume energy losses through the hole are negligible. And we want ht, so that is the height of the water in the tank as a function of time. And then I give you some conditions and say, given that, how long will it take for the water to drop to 2 feet? Give a second. I'm going to draw a little picture. Okay. I'm going to call on somebody to tell me what they did first. And let's see. Nicholas Jones, I see you writing. What was the first thing you wrote down?
My audio is really bad.
Oh. Okay, sorry about that. Let's do Seth Tracy. What was the first thing you wrote down?
Well, the very first thing I did is I drew a picture.
Yeah, they're great.
Yeah, but then the second thing that I did was I wrote down, the equation that we just had, that 0 is equal to m in minus m out.
Okay, but is that equation valid now?
Oh, wait, no, you're right, because dm is changed.
Because now it is not steady state. That's the difference. All right, so the dm dt doesn't go away. In minus m dot out. In this case, dm dt, this is what we would call the mass inside our control volume. But practically, what that means is, say that the control volume, is just around all of the water in the tank. So as the water drains, the control volume is also going to shrink. Okay. All right, so just talking about the control volume is just a way of thinking about that. it's the same as just saying the water in the tank. There is a simplification we can make here. What is that simplification? Christian says there is accumulation in this. Yes, exactly. There is accumulation in this. Technically, it's, I don't know what the word for the opposite of accumulation is, since it's dropping, we're getting less and less, but we use the word accumulation for that, and it can go positive or negative. But yes, there's accumulation here. It is non-steady state. So simplifying assumption we can make right now at this step. I'm going to call on somebody. How about Avonlea?
Hi.
Hi. What do you think a simplifying assumption we can make is?
Determine the height.
Okay. Just right here on this step, look at those the three things we have right now. What can we do right now that simplifies this?
I mean, considering the dimensions we have, we might want to assume constant density and make it in terms of volumetric flow.
All right, that is actually really good, and we are going to get to that. That's perfect. Connor says M in is 0. That's what I was fishing for, though what you said is also right. That's what we're going to do next. M in is 0. There's no water flowing in. You could have a situation where there's water flowing in and out at the same time. Imagine like a bathtub, and you have water going into the bathtub from the spigots, and then the drain is unplugged, so it's also going out at the same time. And so then the water level could be building up, or it could be draining down, depending on the relative rate. But in this case, there's no m dot n, only out. So now we're going to do what Avonlea said. And this step is a common step that will be very useful. So and what we're going to do now is we are going to assume incompressible flow. That means constant density, and we're going to pull the density out of this, and we get rho times dv dt is equal to negative rho times v dot out. And since it's incompressible, we know that the density is going to be essentially the same, both inside the tank and flowing out of it. So we can just boom, boom. And we end up with dv dt is equal to negative v dot out. And this is something that happens whenever you have incompressible flow, is that the mass balance actually reduces down to be a volume balance. All right. So we've got our volume balance. Let's remind ourselves what we're trying to find. We are trying to find the height of water in the tank as a function of time. I'm going to give you all a second to think about it. And then I want someone to tell me how they think we're going to bring in height. Giving you a second to think about it. Okay. Christian says rho GH. That's a good idea, and we're gonna get there eventually. That's gonna come into play eventually. It's not what I would do next, though.
Could you replace the volume The volumetric, or the volumes with the relationships with the heights. So like dV would equal pi r squared h.
That sounds good to me. So remember, this is a tank like this. And so the shape inside there is a cylinder of water. And so dV dt is going to equal d pi r squared h dt. And then the out is going to equal negative the velocity out, or negative the area of that out of that little hole, velocity out, like that. Okay, this is a cylinder, so it's pi r squared h. Now, so we have pi r squared h inside that derivative. Anything that's a constant can come out of the derivative. So what's a constant? I'm going to say.
Because it's a cylinder, we would know that the radius would be a constant, and then pi is always going to be a constant. So we just
All
be
right,
left with
pi
the
is always a
dH/dt.
constant and radius is a constant. In this case, because it's just a cylinder, just straight up and down. In your homework, you're going to do a problem where r is not constant. That's going to be fun for you. Okay, we'll pull that out. We get pi big R squared dH dt is equal to negative pi over 4 d squared. Just using d here because that's what the problem gave us. It said a hole of diameter d times that velocity, which pi's go away. Okay. Okay, and I'm gonna go ahead and just put dH dt on this side, and negative 1/4 d over big R squared, well, V naught. Okay, so now we have a nice differential equation of h with time, and we want h as a function of time. All right, I see something interesting coming on in the chat. Oh, some people are saying that V naught is going to change. Yes, it will. Good job. All right, V naught is going to change as the height level of the water drops. Okay, and so that means that V naught is going to change with, if anything in here is changing with either, if it has a relationship we know with either height or time, we have to put that in before we integrate. So again, I'm going to give you another second. In fact, I'm going to give you a little bit longer this time. And then I'm going to ask someone for some expression for V as a function of H. I'm going to ask you for and you have the tools to do that. So I'm going to wait for about a minute and then ask somebody. Minute and a half. Okay, Tyler says we can still assume the velocity at the top of the tank is 0. All right, that is a good question because the whole point of this is that we are assuming that the level of the tank is changing with time, right? But because the area of the tank is so big, okay, the level will be dropping, but it's dropping because the area of that tank is so big, we will assume that velocity at H, I'm going to call that VH. Is close to 0. Okay. So yes, we're still making that assumption. We're saying that over any, little piece of time, the velocity of that dropping water level is going to be really small compared to the velocity coming out the bottom. And that comes from that area being really big compared to the area of the little hole. Assume, I'm gonna write the assumption out. All right, so Zach gives us V naught. Zach tells us, let's actually go to the next one. And he said V naught is equal to square root of 2g h minus h naught. All right, and that is good. I would probably say set h naught is equal to 0 and just get rid of that. There might as well, but yeah, that's right. So Zach, how did you find that?
I just used the mechanical energy balance.
Okay, you just used the mechanical energy balance. I'm going to write it out because I want to talk about a couple other assumptions that we had to make to get there. So the mechanical energy balance in its complete form is like this. Oh, rho G, sorry. All right, so obviously there's no pump here, so that just goes away. I said we're going to assume P1 is about 0. P2 minus P1, why does that go away?
They're both atmospheric.
Both atmospheric. Okay. Alrighty.
If the hole wasn't open to the atmosphere, would the bottom pressure be rho GH?
Yes, it would. If it wasn't, though, if it wasn't for the atmosphere, it wouldn't be coming out, right? Though I guess maybe you could have, yeah, there has to be some kind of pressure difference to make it move. If it wasn't open to the atmosphere, it would just be a tank full of water. And in that case, yes, the bottom pressure would be rho GH. Alrighty. One other assumption, what's the other assumption we make? Zach, what other assumption did you make at this point?
I assume that losses were negligible.
Yep. Assume losses are negligible. In real life, there's an exit, and whenever there's an exit, there's going to be some loss, but let's assume it's negligible, which it will be most of the time. Yeah, it'll be close to negligible. It's a pretty good assumption. If instead of just a hole, we had a long hose, so it flowed out through a long hose, we would not want to assume losses were negligible, okay? Because there would be all those major losses there. Now, one of the reasons I wanted to bring this up is because there's another assumption here that we talked about many moons ago, and then mostly did not talk about, and I bet you have all forgotten. Does anyone remember what alpha is?
That's the kinetic energy correction factor, right? So,
Kinetic energy correction factor, yep.
so we probably just assume that that one is 1 and that it's flowing turbulently.
Yep, that is exactly right. So alpha is about 1 for turbulent flow. So we are also assuming that flow is turbulent going out that hole. And I bring this up because it's going to come up onto your homework. But the essential point is that this equation we set up is only going to work while the flow through the hole is turbulent. That actually means when it gets really, really low, when the water level drops really, really low and the velocity gets really, really small, it'll start to be laminar and this equation won't work anymore, but it would have to drop quite small. So this equation we're making is going to work for most of the time it's draining. If it drains far enough, surface tension becomes significant too. That's a whole thing. Yes?
Can I ask a question? Okay, so when I started, I was saying like, I was trying to think of it as more of like a like, I knew that the velocity would be equal to kind of, oh wait, I think I did my equation wrong. Never mind.
Okay. All right, so you just set it up wrong, but it's just the same problems we've been doing this whole time. Okay. And you end up with E naught is equal to square root of two G.
Okay, wait. I think I figured out what I was doing. Can I ask a question about it? Okay. So I did d v naught dt is equal to a dh dt over still d squared.
Okay. So you said, sorry, could you repeat that to me again?
Yeah. So I did. Well, I guess it could just be v naught equals a times h over d squared.
H over d squared?
Yeah.
How did you get, where did that come from? This isn't the right units. That's going to be in units of length. This is going to be, meter squared, meter squared. It's going to be meter. So where did that come from?
I was thinking like the area. Oh, sorry. It would be like a height drop per time, I guess.
Yeah, it is a height drop per time. That's what we're trying to find. So there is a height drop per time. We don't know what it is yet.
And then that's why you have to use. Okay, that makes sense. Thank you.
All right. Yeah, and it's because, so when the water is super high, when the water level is really high, you're going to get a really high height here. That means a really high pressure down at the bottom of the tank, and it's going to flow out super fast. And then as it drops lower and lower, and the height goes down, then the pressure at the bottom of the tank will be less, and the velocity shooting out the hole will slow down too. Okay. Till eventually it'll just be trickling out. Okay, so we have an expression for V as a function of H. Let's put that into what we already had, which was something. dH dt is equal to negative 1 over 4. I believe it was d over r, yeah, little d over big R squared. Okay, times V naught, which is square root of 2GH. I'm going to check the dimensions on this real fast just to make sure everything's right. This will be length per time squared That's length squared times squared. Square root that and you get length per time. This is going to be unitless. So we have, because it's just length over length. So we have length over time right here, and it's dh dt. So that should be length per time, right? Because height is dimensions of length. So length per time, we're good. All right. To check that real fast to make sure it makes sense. All right. So now's when we separate and integrate. I'll do, I'll choose. There we go, that should work. All right, all of that is constants, dt. All right, so now let's give you a little minute or so to integrate. Oh, wow, that took longer than I thought. We're at the end of the class, so I'm just going to go ahead and do this. 2h to the 1/2 integrated from okay, so we do this integral, and I'm going to integrate from 0 to t, and I'm going to integrate from h naught, which is what the height is at time is equal to 0, to h, which is what the time is whenever. Okay. Zero to t. And so we get, see, h to the 1/2 minus h naught to the 1/2 equal to, I'm going to go ahead and put 2 over on that side, negative 1/2 d over r squared square root of 2g t. And we get, at the end of my slide, okay, we get h is equal to, let's see, negative h naught to the 1/2 minus 1/2 d over r, and I'm sure I could simplify this and make it prettier. Square root of 2g t. T is outside of that squared. There we go. It's height is a function of time. And just to check, at h is equal to 0, at time is equal to 0, this will be h naught to the 1/2 squared, which will be h naught. That checks out. And yeah, okay. It's supposed to be 1/2 or 1/8. Yeah, it should be 1/8. You're right. I know. Instead, there might be some other simplifications, like I could turn that big R into a big D, or there might be other things, but there we go. And then we could, in order to find the time at which height is whatever I said, then you could solve this equation for t. T is equal to blah, 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 h, plug everything in, and you would have the time it takes to get to that height.
I have a quick question about the very beginning. When you pulled the h out of the square root of 2gh, is that just like a property that you can pull it out? Because I thought you had to take the derivative of the entire thing.
Okay.
And end up with like a different.
Square root of A times B is the same as the square root of A times the square root of B.
Okay.
All right.
Okay.
So that's what I did. I turned square root of
Simple property.
2gh into square root of 2g times square root of h, and then divided h over on there.
Perfect. Thank you.
All right. So your homework, you have 2 transient mass balance problems. I don't think either of them is that ugly. There's some really ugly ones you can get if you have an m dot in and an m dot out and lots of stuff. But they will require you to think about it. And so I suggest starting early and then coming to my office hours or TAA's office hours if you have questions. Because this is like the golden example of one of these problems. As I said, you probably did this in your calculus class. You may have forgotten, but you probably did. So I suggest starting that homework early so you can think through sort of the ways of thinking about it, coming and talking to us if you need to. Also, there is a quiz that will open at midnight and last until midnight Wednesday. I will also post these slides with my writing on them. I apologize, it's not neater, but hopefully it will be helpful. And the video, there is some possibility there's an algebra mistake in here. I don't, because I didn't write down the answer before class, but I think it's right.
If we know that H naught is always 0, are we allowed to exclude it symbolically from the final answer if we show that it goes to 0?
H is z equals 0. You can put z equals 0 wherever you want. And there's no reason not to put z equals 0 there, and it makes it nice. So in that case, yeah. If you'd like, you could put, when you say h is the height in the thing, I feel like it kind of implies that we assume z equals 0 at the bottom. I sort of feel like that's implied when you say the height of the water is 10 meters, you mean it's 10 meters above the bottom. But you could also write z is equal to 0 right there. Or you could write z equals 0 at bottom of, assume z equals z2 is equal to 0 or anything like that.
But what I'm talking about is like in our final answer, we have h is equal to h naught to the 1/2. We know h naught is 0. Are we allowed to say that goes to 0? I'm not going to include it.
All right. So I made a mistake calling this h naught. I should have called that h2 or something. H naught in here is the height at time is equal to 0.
Okay.
All right. Sorry, so that was my mistake because I wrote down h naught to mean 2 different things, which you should never do. Here, in this integral, h naught is the initial height of the water, which, for example, is 4 feet here in this problem. So that's h at time is equal to 0, whereas I just said that the height at the bottom where the flow is going out is 0. I could have also called that like C2. That would be fine, yeah. All right. Any other questions?
I have a question on the previous slide.
All right, this one.
So at the third step, in which case we have our derivatives in terms of volume and time, what stops us from integrating at this point?
Well, because, so this one right here.
Yeah.
Okay, what stops us from integrating at this point is that v dot out is changing with time. So it itself is changing with time. We know it is because as the height drops, as we talked about, the pressure in the bottom of the tank is gonna lower, and that's gonna change the velocity through the hole, and that's gonna change the flow rate through the hole. So we can't integrate with respect, so if something in this equation changes with time and we haven't plugged that relationship in yet, we can't integrate with respect to time yet, or the integration won't capture how that change.
Okay.
Mm-hmm.
I'm just thinking about with other classes when we've done this before. I guess in those cases, that the volumetric stays the same.
Exactly.
Well, just here.
Okay. If it's a situation where we can assume that v dot out is constant, then you could do that, because then it would just be a constant and you can just integrate.
Okay.
And over a very small amount of time, even this problem, you could do that. But in this case, the whole point of it is that we're watching over enough time that we can see it draining out. And so, yeah. Okay, thank you. I do appreciate, by the way, that y'all stay after the 11:50 mark. I feel bad because you are, even though it's online, you are technically out of class now, but I appreciate you stay and ask questions. I really appreciate being able to talk to you about it. Okay. All right. I'll post all those things that I said I will post, and I will see you soon.
Thank you, Dr. Nickerson.
Thank you.